Hi everybody, and thank you for joining me today. What we're going to be doing is an example for proofs by induction. And what we're going to prove is that 2 to the n is less than n factorial, where our variable n is only greater than or equal to 4, and n is within our set of natural numbers. Now, in the video that this example is linked in, I talk about what it means to be a natural number. So let me just give you a really shortcut version of it. So the formal way to describe a natural number is to say that it's a positive integer, which means it's a whole number and it's greater than 0. The reason why I don't like to describe natural numbers as positive numbers is because sometimes a lot of people forget that 0 is not a positive number. A lot of people will lump it in and then you mess your whole thing up. So we know that natural numbers have a starting point, and that's because they follow something called the well-ordering property. And all that means is that the natural numbers themselves have a starting point at 1, because that's the first number you can actually count to. So they have a starting point at 1, and we know that any subset or little group that we take out of the natural numbers also has a starting point. For example, if we look at even natural numbers, they start at 2. Odd natural numbers happen to also start at 1. Prime natural numbers start at 1. They all have a starting point, and that's what we're going to use to do our basic step. All right, so let's get started with our basic step. It can also be called a base case. It just means that we're going to start at the beginning. So the way induction works is your first step, you want to prove that it works for your starting point, right? Because remember, the reason why we work in natural numbers when we're doing induction is because they have a starting point. In our case, our starting point is going to be 4. So we're going to say let n be equal to 4. And then we're going to plug it into our equation, which is 2 to the n is less than n factorial, which is going to become 2 to the 4th is less than 4 factorial. You can plug it into your calculator, you can do it in your head, but at the end you're going to get the result that 16 is less than 24. And of course we know this to be true because we know how numbers work, and 16 is less than 24. So what you just did was you proved that this theory, 2 to the n is less than n factorial, that works at our lowest number.
So before we get into our inductive step where the real magic happens, I just want to take a little bit of time to explain exactly what induction is. So as you guys know, we just proved with the basic step that our theory works at our starting point. 2 to the n is less than n factorial at our starting point, which is 4. But if you only know it works for one number and there's an infinite amount of numbers, you didn't really prove much. So again, following the well-ordering property, we know that n and any little group we take off of n has a lowest term. Great, we have a starting point. But the lowest natural number is 1. So that means that to get from one natural number to the consecutive number, you add 1. So if I want to go from 1 to 2, I add 1. This is important because it's going to allow us to do something that is pretty much a miracle in my opinion. We're going to be able to prove something for an infinite amount of numbers. So, like I just said, the way you get from one number to the next in the set of natural numbers is by adding 1. Now, you can also get from one number to the next by adding 10, but you skip some numbers along the way. And that's not okay, because if we can prove that it works for every 10 numbers, we didn't necessarily prove that it works for all the numbers that are in between. So the inductive step is the step where we say, let's look at infinity. And because the natural numbers are an infinite set, any number you think of, I can tell you one that's bigger. You'd think of 1,000, I think of 1,000,000. But again, let's not go that big because we skip a lot of terms. So if you say 1,000, I'm only going to say 1,001. And that's the theory we're going to use in induction, is that we just proved that it works for the lowest element. Now what we're going to do is we're going to try to prove that it works for the next element, the eternal next element, if you will. Our variable is n. So with induction, we're going to show that it works for n plus 1. Because if we know it works at our lowest point, which is 4, we just proved that in the basic step, and then if in our inductive step we can prove that it works for n plus 1, well, then we just proved it works for 5. And if we know it works for 5, and we know it works for n plus 1, then we know it works for 6, and so on and so forth. I think it's an absolutely beautiful thing. Induction amazes me. But with that being said, let's get on to actually doing some induction. So the way that we're able to do induction, like I just said, is we prove that it works for the first term. So we're going to say that we have a statement. We'll call it P of n. And we're going to say, let P of n be true. And P of n is the fact that 2 to the n is less than n factorial, where n is greater than or equal to 4. And we assume this, working off kind of what I just said, where we know the least element, so we build our way up. We need to assume that it's true, that P of n, that it works for n. Because if we know it works for n, we're going to use that to show that it works for n plus 1. So let P of n be true. Okay, well, I know that I want to find out what this is for n plus 1. So all I'm going to do is plug in n plus 1 for n. So we're going to get 2 to the n plus 1 is less than n plus 1 factorial. Now I know this looks messy. And when I first saw it, I'll admit, I got kind of freaked out too. But just use a little bit of brain power. It's not as bad as it seems, I promise. So we know that 2 squared is 2 times 2. And 2 cubed is 2 times 2 times 2. So what's 2 to the n plus 1 equivalent to? Well, how do we get from 2 squared to 2 cubed? All we did was multiply by 2. So to make our lives a little bit easier, we're going to rewrite 2 to the n plus 1 as 2 multiplied by 2 to the n, because they're equivalent. And I'm looking at this n plus 1 factorial, and it's freaking me out. But then I remembered, what does it mean when something's factorial? Well, it means that you multiply all the terms that come before that and that term. So 4 factorial is 24 because it's 1 times 2 times 3 times 4. So I don't know anything about n plus 1 factorial, but I assumed my P of n was true. So I do know something about n factorial. So again, how do you get from one number to the next in the natural numbers? Well, you add 1. So n plus 1 factorial is really just equal to n plus 1 multiplied by n factorial. Cool beans. So we have something, and the more I look at it, the more I realize my P of n is in here. I see that 2 times 2 to the n is less than n factorial times n plus 1. Well, again, from my induction assumption, I already know that 2 to the n is less than n factorial. What I care about now are the coefficients. So I know it seems odd to kind of drop out some terms, but because we already have assumed that and we know that 2 to the n is less than n factorial, we just need to make sure that the coefficients aren't so big or so small that they really throw us off. So we're going to guess that 2 is less than n plus 1. Now, n is our variable, and if you've taken any algebra courses, you know that we like to have our variables all by themselves. So you subtract 1s from both sides, and you get 1 is less than n. And that statement is definitely true because the only numbers we are looking at are greater than 4. So with this, we prove that our coefficients aren't too big or too small. They're not going to throw off what we already know. And we just proved for an infinite amount of numbers that 2 to the n is less than n factorial. That's amazing to me. The fact that simple little algebra tricks can be used to uncover things about infinity. Infinity is bigger than anything you could ever imagine. It's just beautiful to me. Thank you so much for joining me today, and I hope you enjoyed listening to this just as much as I enjoyed making it. Have a great day.